welcome to everyone. It's a good audience, and I think we made the right call because certainly trains around here aren't running, and the snow wouldn't have helped either. So um, it's very interesting time we're in with these lectures, and I'd appreciate any comments from anybody about what they think we should do best. But we will run this one, and an even greater thanks is owed this evening to Fred, because our speaker was going to come from Belgium. We thought there was a fair chance he wasn't going to get here anyway, and if he did, it would be quite embarrassing if we couldn't get there to listen to him.
Half an hour chat first.
We made a call that said we would run this as an online meeting, and thank you for signing up, and thank you for turning up, because it's always nice that when people do sign up, they actually appear, because it's a bit of a disgrace when we don't have an audience for our speaker. But Fred, I hope we have a good evening, and thank you very much, as I say, for standing in at quite short notice and hopefully delivering something that will make us all think a bit before we go to sleep tonight. Fred's pretty well known, but Dr. Fred Starr, we always think of him as a metallurgist. He graduated from what is now the University of Surrey, Battersea College, in 1966, and joined British Gas, and for a long time worked there. And when the British Gas research changed dramatically, he moved on to the European Joint Research Centre in the Netherlands and did some work on hydrogen from coal and so forth. He says, despite this, he is extremely cynical about the hydrogen economy. I'm not sure that I associate the word cynicism with Fred. He's critical, and he makes good analysis of things and doesn't necessarily just go with the party line. And I think that's what we'll hear tonight, and that is always very welcome in my book. So Fred has done some great service with the Newcomen Society in terms of running conferences, and of course our last summer meeting that we held 4 years ago, nearly now, over 4 years ago, isn't it, on Teesside. And so I would like to just pass this over to Fred and say thank you very much again, and we look forward to hearing your views on Concorde and engineering failure, however you define that, but we'll pay attention and listen, Fred.
Right. Okay, well, we've got a lift off, or whatever Concorde used to do. It talks about Concorde, as you see, the greatest looking plane ever. I would not disagree with that at all. But I think looked at objectively, it's an engineering failure. And I've got to explain exactly what I mean by an engineering failure. There's a huge amount of hype about Concorde, and this photograph that you see in front of you typifies it. It appears to be showing Concorde just about to break the sound barrier at around about 30,000 feet. If you look very carefully, you see it's a made-up picture. The tail wheel that Concorde had, because it had to have, because of the way it took off, is out, and the nose is down. That peculiar nose is down. This was taken from somewhere over an airfield and then put on, photoshopped on top of a cloud formation from a very high altitude. And you get this kind of half-truth coming about Concorde all the time. Next picture, done. Thank you. Next slide, Dan. Ah, right, here we are. Just go back, Dan. Thank you. Well, I've broken the talk into 5 pieces. Supersonic aerodynamics are really quite peculiar. They're different to a lot different to what people think. going to talk about the Olympus engines, principally that they really weren't man enough for the job. When I talked down at Bristol, I took my life in my hands by saying that Olympus engines were really not man enough for Concorde. When I did the talk at Cardiff, it was to a metallurgical bunch, and I talked about the aluminium alloys being not good enough. Those two things led into Concorde's range problems. Concorde's aerodynamics probably couldn't be better, as I'll mention in the final topic, the SR1 71 Blackbird, which flew 50% faster than Concorde. But again, it's not quite as good as everyone thinks. And then the supersonic business jets, which are going nowhere. Okay, Dan? When I talk about engineering failures, I don't talk about disasters like the Tay Bridge, which blew down. Chernobyl was the most horrific disaster. And we have Mr. Putin promising to give us another disaster soon. And then we have the Concorde disaster itself. I'm not talking about those things. Okay, Dan? I'm talking about engineering failures. Equipment that looked absolutely great, but actually didn't go anywhere. We've got Brunel's Great Eastern. I'm glad that Julia is here tonight, because I'm as critical about Brunel as almost as much as she is. One of the problems with the Great Eastern was it needed two different sets of fuel-hungry engines, and it didn't manage to do the kind of length of voyage that Brunel was hoping for. Okay, Dan? Then we have the advanced passenger train, which was supposed to do 150 miles an hour between London and Glasgow. Now, it's going to rely on gas turbines rather than having to use electricity. That was going to be cheap. But gas turbines, small gas turbines, very inefficient. To get around the curves, they had the tilting mechanism. Neither of these worked very well. The fuel consumption of the gas turbines was very high. The train was launched at a time when fuel prices were going through the roof. The tilting mechanism didn't always work. And when it worked, and this is something which I want to emphasize a bit, there's often something with an engineering failure that you never thought about. And the fact was that when the tilting mechanism did work, it worked in such an abrupt manner, it made passengers think that they were on a roller coaster, and it made them sick, particularly if you had been a group, 100 boozing journalists up in Glasgow the night before you were coming back on the train from Glasgow to London. Okay, Dan? And then we have the advanced gas-cooled reactor. This really failed because there was no standard design. But there were two things that they didn't really think about when or thought there would not be too much of a problem. The breakaway corrosion of the superheater and boiler tubes. I mentioned that kind of thing in my oxidation talk a couple of years back. The latest thing which is killing the advanced gas-cooled reactor is that the graphite bricks, which are used to moderate the velocity of the neutrons, are cracking up. And when I took this picture, I was told that Dungeness B would last at least another 10 years. It's been taken out of service because of the graphite bricks problem. All of these three things I just showed you look absolutely magnificent to the man in the street and the politician and some businessmen who were underwriting the costs, but they were engineering failures. Dan? Well, some types of engineering failure occur because they take too long to build and the construction cost is too high and the market and political interest changed. Concorde suffered from all three of these, but I don't want to concentrate on those tonight. Dan? They look great when they were built, but Dan? The critical features never properly functioned. We had unforeseen operational problems became a major issue, and the unforeseen operational problem that became a major issue was the sonic bang and airport noise for Concorde. Those became very serious issues, which were brushed aside when the enthusiasts started on the task of building a supersonic transport. But the main problem with Concorde, I think, which was again led to very low sales, was that target specification in terms of range became impossible to meet. Okay? No one bought another. Only the French and British airlines were forced to buy it. Now, one of the peculiarities I mentioned at the start, one of the peculiarities about supersonic transport, it is absolutely unique in forms of transport. In that, if you look at this graph on the left-hand side, you'll see passenger miles per gallon. At the bottom, you've got Mach number, the speed of sound, in terms of the speed of sound. And it's a unique form of transport in that the faster supersonic aircraft go, the more economic they are. And it's one reason why Concorde strove to go just above the speed of sound, Mach 2.2. That was the limit of the aluminium alloys. And the Americans went for Mach 2.7. Both of those slightly peculiar numbers, neither Mach 2 nor Mach 3, are dictated by the limitations of materials. Okay? Going faster is more economic, but faster means hotter. Okay? And what happens is that as supersonic aircraft go faster, they get hotter and hotter, essentially due to air friction. And we see on this graph that at Mach 2, Concorde would be getting up to 100 degrees, and at Mach 3, an American supersonic transport will be hitting something like 250 degrees. These don't sound very high temperatures, but if you want to build an aeroplane out of reasonably lightweight materials, neither aluminium nor titanium have got terribly good high temperature strength. Okay? Now we come to the sound barrier. This is one of my favorite pictures. It's from a 1952 film in which one of the heroes is about to try and go through the sound barrier, and there's a lot of things in the press at that time about how dangerous this was. And with the aircraft that they had at the time, it was indeed dangerous. Dan? It was dangerous because aircraft, when they reach the speed of sound, tend to go into a dive, and they go faster and faster, and they can't recover from it. Concorde gets over that problem by pumping the fuel to the back of the aircraft to basically balance the aircraft out. We have increased drag at supersonic speeds and aerodynamic heating. Okay? Now, we've really known about sound barrier for a long time. Benjamin Robbins investigated how fast musket balls would travel by putting various amounts of gunpowder into muskets. And he found that when a musket ball reached around the speed of sound, the aerodynamic drag became very, very high indeed, much more serious than simple Newtonian mechanics would suggest. Okay? And Professor Ernest Mach, where we get the name Mach numbers from, he was the first to photograph shock waves. Okay? When you create a shock wave, these are these V-shaped things around the bullet in the picture. There's a drop in the velocity of the air behind the shock wave, increase in temperature and pressure, and that's basically wasting energy. That appears in the form of drag. Okay? Big increase in drag. Okay? You can't normally see shock waves. You can, if you're on a something like a 747 on a transatlantic flight, if you're right in the right position, you can just see the shadows of the shock of the expansion wave over the wing. This is a very clever picture showing two Northrop F5 flighters flying over the ground. It was done by taking a picture of the ground and then taking a picture of these planes going over it. And because of the change in refraction across a shock wave, you got this, you could actually see the shock waves in the photographs. Okay? Now we come to a bit of aerodynamics. The big thing in aircraft is not actually the drag as such, because you'll always get drag when you're pushing a body through the air. With aircraft, it's the lift to drag ratio. The lift is simply the aircraft weight. The drag is how much resistance you're getting from the air. And the engine thrust has got to equal the drag. So you actually want as little drag as possible. And that appears in a function called the lift to drag ratio. You want that as high as possible. Go on, Dan. It was the aerodynamicist F.W. Lanchester who came up with this analogy. He said the lift to drag ratio is critical in aeroplanes, and it's just like climbing a mountain. Well, this gives you an idea of what the mountain that Concorde has got to climb. Going from London to New York, its effect with Concorde has got a lift to drag ratio 7 to 0.14, and it effectively is climbing a mountain 462 miles high. That tells you why we need such a lot of fuel. That's, probably about 20 times higher than any mountain on the earth. Okay. Now, the progress of aircraft design has been through the ages, or through the years, getting better and better lift-to-drag ratio. Now, the Wright Flyer, the reason why it was successful, it had an incredibly high lift-to-drag ratio of 8:1. It didn't really need very, very much power to push it through the air. The DC-3, Dan, click, of the 1930s, the lift-to-drag ratio was 14.7:1. Okay, Dan? The aircraft, which we might remember as kids, the piston engine aircraft, Super Constellation, one of the first really good transatlantic planes, 16:1, and here we are. Dan? The Boeing 707 replaced the Constellations and the DC-7s, lift-to-drag ratio of 19.5:1. But look at this, the Airbus, I think 60 years after the Boeing 707, is really no better. We've actually reached an impasse in terms of aerodynamic design. So what about Concorde then? Well, it's actually less than the Wright Flyer, which indicates some of the problems that supersonic aircraft have got. Okay, Dan? Now again, I keep on the aerodynamics. The lift-to-drag ratio of any aircraft is not constant. It changes with the speed. At low speeds, the lift-to-drag ratio is not very good. And for Concorde, it is abysmal. It's got a lift-to-drag ratio of round about 4:1. In other words, if Concorde weighed 400,000 pounds at takeoff, it would require 100,000 pounds of thrust to get it to keep it in the air. The faster it went, the better the lift-to-drag ratio. So as you get up to just below the speed of sound, its lift-to-drag ratio has got to around about 11:1, which is a lot better, of course, but it's awful compared to the subsonic jets. Dan, if you wouldn't mind. Then as it hits the transonic range, because of the formation of the shock waves that I mentioned and the excessive drag that they give, the lift-drag ratio stays the same. But once you reach about Mach 1.2, the lift-to-drag ratio stays the same. Done? I think that's right. The engine thrust essentially stays the same. So, okay, Dan. And this is why you get this very peculiar graph in which the faster you go, the more economic is the aircraft, because after about Mach 1.2, you don't need any more thrust, but so you're not burning any more fuel, but you're going faster and faster. Okay? Faster you go, the less fuel is used. Okay? Now we move on to the engines. Well, the engines that you need for supersonic aircraft are quite different to the ones that you see on the aeroplanes flying overhead. They have to be what are called pure turbojets. They don't have these huge fans in front. The pressure ratios have to be modest. They're around 10 to 1, not 40 to 1. Now, what do I mean by a pressure ratio? Well, that is simply the difference between atmospheric pressure and the pressure inside of the engine just before the turbines. A supersonic aircraft likes to have a pressure ratio 10 to 1. That's all tied in with the fact it's flying very fast. Whereas the fan jets have to have a very efficient gas turbine and they need a very high pressure ratio. Because they're pure turbojets, they're very noisy. Okay? Now, Britain had a genuine supersonic engine. This was created by Major Halford of de Havilland, an incredible engine designer. Started off on small piston engines, then went to large piston engines, then to gas turbines, and then to this. And here we have the gyron. I saw this when I went to the de Havilland Museum about 3-4 months back with Roy Wilson and Fred Barker. Extremely high thrust for its time, 20,000 pound thrust. The right sort of pressure ratio, 6 to 1. Very low weight and quite a small diameter. Okay. But the gyron was junked. The gyron was intended for a supersonic bomber, and the British government decided we didn't need any supersonic bombers. So the gyron went west. The only engine that was at all suitable was the Bristol Olympus, which was first ran a couple of years before the gyron. But you see its thrust is only about half that of the gyron, 11,000 pounds compared to 20,000 pounds. The pressure ratio is about right. It's come out at about the right weight, and the diameter is a little less than the gyron. Okay. It got its power pushed up to 20,000 pounds by 1962 to go into the Vulcan bomber. But Concorde would have needed 6 engines like this, not 4. They needed a lot to get a lot more thrust from this item of equipment. Okay. So there was a major redesign, and they got the thrust up to nearly 35,000 pounds. The pressure ratio, in my view, was on the high side. The weight had doubled, and the diameter had gone to 48 inches. I think that money might have been spent on the gyron to better effect. Okay. Now, Concorde required a lot of thrust. When the initial Concorde proposal came out, the weight of the aircraft was £250,000 pounds. That's when 6 Olympuses might have done the job, but that was just the initial proposal. Okay. When they actually got down to work, The prototype had gone up by £50,000 to £304,000, and then more work was needed. And so the aircraft, which actually was flown, first of all, weighed £367,000. So you actually needed a 1.46 thrust increase over what they originally hoped, because the thrust required is proportional to the square of the weight. All the way through until we reached the final version, which weighed £408,000. So you're talking about a third increase in the weight. You needed a 1.8 thrust increase. Well, how did they actually do? Okay. Well, the blue part of the curve with the sloping curve is showing you what they were doing to get the military Olympus up to higher power for the more advanced versions of the Vulcan bomber. And they reached £20,000. As I said, that was nowhere near enough good for the Concorde. So Dan, they then had to start really overhauling the design of Concorde, almost a new engine. They had to incorporate afterburning, and they reached, as I say, round about £38,000 on the test bed. Okay. Combination of engine modifications and afterburning. They just about got the 1.8 increase in takeoff power that they needed. Okay. But all of this meant huge increase in the takeoff and cruise fuel consumption and aircraft weight. The engines had got heavier, more fuel was needed, and that's deadly in terms of aeroplane design. We're now on to materials. Now, a lot of people say that Concorde reached its design targets. Well, it bloody well didn't. This is what they were talking about in the middle 60s. Mach 2.2. In fact, the man behind Hooker, the man behind the Rolls-Royce Olympus, said, in effect, you shouldn't let the speed drop below Mach 2.2, otherwise it will be disastrous for economics. Flying at Mach 2.2 implies reasonably high temperatures in terms of what aluminium can take. You see the nose is up to 153 degrees and the leading edge of the wing is up to 130. Okay, Dan? Well, this is what we got when you actually were flying it. They dropped the speed to Mach 2.04 to keep down the temperatures, nothing more than that. All the temperatures dropped by 30 degrees, which may not sound an awful lot, but I can tell you, as a metallurgist, small changes in temperature for materials which don't have a lot of high temperature strength are really critical. The noses dropped down from 153 degrees to 127, and the leading edge of the wings has dropped down to 105 degrees. That's done by flying slower. Okay. This is a tensile strength curve. Actually, Rolls-Royce didn't publish this curve. I had to get it from the Americans. And okay, Dan, at the kind of low speeds, you see that the material is running at something like 380 megapascals strength. If it goes to Mach 2.2, it's dropped down an awful lot to about 340. Because of the increase in weight, they had to drop the temperature down to Mach 2.04. Okay? And so we now start seeing the vicious circle of Concorde weight increases. Done. Increased aircraft weight means increased stresses on the structure. Okay? The aluminium alloy was too weak to take those stresses. Okay? Had to fly at a lower temperature. Okay? It's flying at less than the optimum speed. And if you remember what I said at the very start of this talk, you want to be flying as fast as possible because that makes your flight more economic. So your fuel consumption has increased. Okay? The fuel has gone up, so you get more increased aircraft weight. Okay? You need more power. Okay? You have to use reheat, which is a terribly bad idea. It might be very exciting, but you're effectively doubling the fuel consumption at takeoff. So you've got more fuel to carry around. Okay? Okay? Engine weight increases because of the afterburners, and you're on this circle round and round and round. It stopped somewhere, and they did stop it at Mach 2.04 and a reduced aircraft range. Okay? So now we come to Concorde's range problem. Now, the official maximum fuel range of Concorde was 4,990 miles. And that range is actually with the reserves, so you can divert to another airport if there is fog at the airport that you're going to or whatever. But this is the Great Circle route shown on the curve. Why couldn't it do Frankfurt to Washington? Because that's 4,660 miles. It's just inside, but in principle, it's possible. Basically, is that you would think that the Germans would snap that up. Frankfurt, Washington, you know, the two important political poles in the world, besides London and Washington. Why didn't they buy it? Well, in order to do that 4,090 miles, 4,060 miles, you had to fly a Great Circle course. And the Great Circle course would cover a lot of Western Germany, the Netherlands, Britain, and Ireland. And you had the sonic bang problem. And because of that, the aeroplane couldn't fly across these countries at supersonic speed. It would have had to take the longer range, and on the map it looks like the longer range is the shorter range, but this is because of the peculiarities of the Mercator projection. And this kind of problem starts to really impact on who would want to buy Concorde. People, airlines wanting to fly over land for long distances, Concorde couldn't fly at supersonic speeds because of the bang. And once they found that out, they simply weren't interested. It wasn't an American conspiracy. It was simply the facts of life. Anybody got any questions at this stage?
Yeah, Simon. Fred, does the sound of the sonic bang attenuate as far as altitude increases or not?
No, they found out at a very early stage it didn't attenuate as much as they expected.
Right.
My recollection, Simon, from involvement at the time was that part of that is around the weight of the aircraft compared with the weight of other supersonic aircraft. Was the intensity of the bang? Does that make sense, Fred?
Yeah, it does. I think so. It does indeed, because the shock waves would have been stronger at the lower speed. Oddly enough, it's one reason. Yeah. It's one reason why. It's the peculiarity of the shock waves, which mean that as you fly slower, you get a stronger shock wave.
Right. So is this why the SR-71 can actually overfly populated areas and nobody seems to notice that it's there?
Well, I think they do notice that it's there, but they put up with it because they're American, citizens.
It doesn't fly on the same frequency. It doesn't fly over you at 3 o'clock every afternoon.
Well, no, true.
Julia.
Well, this isn't remotely a learned question, but I was at boarding school in Bristol between 1962 and 1967, about a quarter of an hour's drive, if that, from where it was all being built. And actually one of the sort of backdrops to my hideous boarding school life, in fact the only interesting backdrop, were the sonic bangs that you could hear at regular intervals. And at some point along the line, a great chunk of the library ceiling here fell down, and it was ascribed to sonic bangs. I'm sure that's not true, but it's a nice story. But it was quite interesting being in Bristol while all that was going on, in fact. And you can hear it, and you could hear it. I remember on one summer night, suddenly, I was standing on Clevedon Pier, and there was this very, very, very faint roar, very faint. And you looked up, and you could see it silhouetted miles above Clevedon Pier. It was very romantic and wonderful.
But you didn't hear a bang?
But at that point, I didn't hear a bang. And Frank and I used to rush into our front garden at 6:30 every night because she would be coming in and you could hear the roar. Set your clocks to it.
Well, let me pass on this anecdote. I was on a 747 going to America, and it turned out I was sat next to a Spitfire pilot. And I was always interested on how fast you could get a Spitfire up to. And I said, well, how fast could you get in a dive? And he said, well, I don't really remember, but incredibly fast. Well, the highest recorded piston engine aircraft was actually a Spitfire, which reached more than 90%. This is recorded, 90% of the speed of sound. Anyway, he said, but they were very fast. And he said that one day he was on the ground and he heard this peculiar bang. He'd never heard it before. And then about a minute later, a Spitfire came out of a dive. And he said, well, did the Spitfire go through the sound barrier? And he said, I've always wondered about that. Well, I always wonder about this story too, because the Spitfire was a great aeroplane.
On a light-hearted note, I was with a friend of mine who was learning to drive. He was doing a 3-point turn in a narrow street near us, and somebody flew through the sound barrier, and front doors opened, and everybody looked at him to see what he'd hit.
Yeah, I've got some data somewhere, Fred, on the high-flying piston engine aircraft, and I'll dig it out for you. But certainly, the problem with a lot of those was, as you got close to the speed of sound, the centre of lift shifted, as it does on an aerofoil, and you basically go into a death dive, and if you try and get out of it, you just break the tail off.
Yeah, that's quite
anyway,
true.
You got your pictures. But
yeah. Well, I've actually just explained this, Dan. What I was saying, just to reiterate, is that the pink or reddish pink line is the Great Circle line between Frankfurt and Washington. It looks in principle like that's something that Concorde could do, but it means flying for almost about 900 miles or so over the Netherlands, Belgium, England, Wales, Ireland. You'd have to fly at subsonic speed, and that cuts about 20% off the range. So you have to go the blue path, which looks the shorter path, but is actually the longer path. So you're adding another 300 miles on top of this and losing range that way, which is one reason why the Germans didn't buy it. Now let's go on to the next slide. Of course, subsonic range, another problem that Concorde had because of the fact that the Olympus engines were not powerful enough, excessive takeoff distance in hot weather. Okay, done. And here is a little table showing the issues that you've got with various airports. Now, let's say Heathrow to Chicago, 3,900 miles. You would think you could do it in terms of range, but there's a terribly long distance over North America, where you have to fly supersonic, subsonic, so you've lost a lot of range that way. Heathrow, Atlanta is on the borderline in terms of range. Again, you've got a long distance overland, and then you've got hot takeoff problems. Well, the reason why you've got a problem with hot takeoff is that because the density of the air is lower at higher temperatures, and I'm not talking about furnace temperatures. I'm just talking about, say, 35, 40 degrees in the summertime. The air density is less. It means that the wings don't give as much lift, so the takeoff distance is longer, and the engines give less thrust. So you've got a problem with Atlanta. Madrid, New York should be very easy in terms of range. Not very far overland, subsonic, so there's no subsonic problem, but you've got the hot takeoff problem in a place like Madrid. Frankfurt, New York, we've talked, and Rome, Washington, well, it's too far in terms of range. A lot of a long period overland at subsonic speeds, and obviously from a place like Rome, hot takeoff problems. This is the kind of reason why Concorde didn't sell. It wasn't an American conspiracy. It was just that when the airlines took their slide rules to the performance of Concorde, it didn't really fit in with what they wanted. Dan? So Concorde was an engineering failure. Well, actually, yeah, up at the top, well, it took too long to build. I can remember the carry-on over it. The construction costs too high. It's soaring away. I honestly think it was a mistake to give it to Bristol. The market and the political interest changed. The big 747 jets came along, wiped out a lot of the market. Okay, Dan? It looked great. Yeah. Critical features never properly functioned. The engines were not powerful enough. The unforeseen operational problems was a major issue, and the target specification became impossible to meet. Okay, so no one bought it again, apart from British Airways and Air France. That's Concorde, an engineering failure. Let's move on. Yeah, okay. Just reiterating what I've just said. Now, here is another terrific looking aeroplane. The SR-71 Blackbird. It's the only medium range Mach 3 aircraft. It doesn't have the range of Concorde. One reason why it doesn't have the range is that just look at what's coming out of the back here. I know that this is a mock-up picture. The afterburners are fully on because it's got this peculiar turbo ramjet aero engine design, in which the jets working like need an afterburner on all the time, which means that the fuel consumption is almost twice as high as what you have in the Olympus engine. Okay? The lift-to-drag ratio was poorer than Concorde. As far as I can tell, we're talking about something like 5-to-1 compared to 7-to-1 for Concorde. So look at it, all of these big engines all over the place, drag-inducing engines, the big tail fins. This is an aeroplane full of drag. Okay. The turbo ramjet engines are fuel inefficient. Okay. What amazes me is that it needs air-to-air refueling immediately after takeoff. Now, Concorde might have been a great success if somewhere over Oxford, Concorde could have done an air-to-air refueling and it could have gone anywhere, but I don't think the airlines would have found it completely acceptable. Okay. And the range is very dependent on air temperature. Something I haven't put in this is that at subsonic speeds, in order to go through the sound barrier, it goes up to 40,000 feet and then dives to get through the sound barrier, and the engines pick up more thrust. Again, I don't think that would be something acceptable in Concorde. Okay. Well, we now come to the joke, the supersonic business jets. There's one set made by Air, which originally were aiming at Mach 1.5. The picture with the straight-winged aeroplane. They then went over to the tri-jet swept wing, flying a lot slower, Mach 1.2, a real knife-edge design, and the boom overture. Dan, please. Here is the passenger numbers, the area AS2, 8 to 12 passengers. Very long range it's supposed to have. The boom overture, flying at a lower speed than Concorde. As I mentioned, the slower you go, the less economic a supersonic aircraft is. 65 to 88 passengers, quite long ranges. These are all made out of composite materials, supposedly an high temperature epoxy and carbon fiber. Both designs need engines. General Electric expressed their interest and then cancelled the program. Rolls-Royce say now no interest. Engines are the key to supersonic travel, transport. And we don't have good engines at the moment. Nobody's designing supersonic engines, okay? And even if these things were built, they would never be allowed to fly. You saw how the Greens blocked the M25. Well, imagine what they would do to these business jets if they found out that flying from London Heathrow to Washington JFK Kennedy, it was going to be something like about 5 times more fuel per passenger than going on a subsonic aeroplane. These planes would never get off the ground. It's a similar story for these other so-called supersonic business routes. Okay. Conclusions. Well, Concorde's aerodynamics were great, but we needed better engines, certainly engines without reheat, and a better aluminium alloy. That's it. Thank you.
Thank you very much, Fred. What we'll do for, if people have got questions, then please, if you raise hands, it helps me when I look at the Muppet show that Dan will flick up, because you'll peek up to the left-hand end and I can see you. While you were speaking, Fred, I just nipped downstairs and went to my library, and I found 2 papers which I will send to you, because these are contemporary of the development, written in 1973, so that they must have left the office when I left British Aircraft in 1974. And what is interesting, just having a quick glance, is that the comparators that were made over things like noise and so forth at that time were, of course, the noise of something like a VC-10, the fan aircraft. The first 47, I remember visiting that at Heathrow in 1970. So what we forget is that aircraft noise has decreased enormously Concorde was dreamed up in the 60s. So the comparator was it makes about the same noise as a VC-10. Well, a VC-10 is a horribly noisy aeroplane by modern standards. So it's kind of an interesting comparison when you look 50 years back. But I'll send these to you and I'll scan them so you can amuse yourself.
I would be really pleased about that, because the papers that I've been looking at are essentially what people were saying before Concorde actually flew.
Right. Well, this is a lecture to the Royal Aeronautical Society by George Edwards in '73, titled "The Technical Aspects of Supersonic Civil Transport Aircraft," and the other one is much more enlightening, which is, I'm not sure whether it's an internal report or whatever, but I've got a copy. It says "Supersonics in the Environment." Well, that sounds like that sounds a bit like certain other things.
It's so good that people like you, like me, have got very sticky fingers.
I know, exactly.
Yes.
Anyway, another hand up is Frank. So, Frank.
Thank you, Fred. That was really, really interesting. So my question is the inference to draw from your talk that the decision to continue with Concorde was actually a political one? Because I remember the press conference where they announced how Concorde was going to be spelt. I remember there were two alternatives: the English spelling and the French spelling, which had an E at the end. And the British minister responsible, and I forget who it was.
Wedgwood Ben.
Was it?
Yeah.
Was it? That's interesting.
Yeah, it was Tony Benn. It was Tony Benn. He was the minister. He was the minister of whatever it was at the time.
In his technocratic phase before he moved rather to the left. Anyway, he said that we're going to have the French spelling because the E stood for Europe, England, and entry. Because at that time we were going through one of our sort of, are we actually part of Europe or not? So particularly entry into what was then the European community was that really so showing that British and French companies and personnel and experts could actually work together on a project to produce something? So are we to infer that people said, right, we're just going to ignore all these technical issues, this is a political project, let's do it? Is that inference to draw from your talk?
Well, I don't think it was initially. It was, I think, initially it was the fact that the Americans had stolen the Mach in terms of subsonic jets, and the subsonic jets that they had at that time were not that economic. It was basically, again, because the engines weren't very good. So if you came along with a supersonic aircraft, if you matched what was going on at the time against the Americans, we could get in, and because we were going for a lower tech aircraft than the Americans, we would get the market before the Americans had really woken up. The Americans went for Mach 3 initially. They dropped it to Mach 2.7. Well, if you go to Mach 2.7, you've not just got the metallic materials to worry about. You've got all of the things like the lubricants, the tires, and everything else, which are getting heated up, flying at something like 250, 300 degrees centigrade. I mean, would you like to go down the road with a tire which was literally twice the temperature of boiling water? And, you're going to have to land the plane on that. So Concorde was, in a sense, a good technical target. Unfortunately, I think the engines were not good enough, and the material construction was not good enough. If they'd both been a bit better, we would have got in there. So there was a political decision at the start from the technocrats towards the end, I think it became more political in the way that you're indicating, Frank,
Right.
in that both the French and the British governments were sort of like arms deep in it and couldn't get out without a huge lot of embarrassment.
I think, Frank, you have to remember that Tony Benn was an MP for Bristol North or whatever.
Yes.
So I remember going down with my then boss who I was working for, who was the deputy chairman, to have a meeting with Tony about this little Soviet he was proposing in our works. So it was an interesting time, but he was very much on this white hot revolution and all the rest that was going on. And I think when you look at the original or the papers that I've got going back some while to the original concepts of Concorde, it was all about speed, and we were very much a generation that was looking to get places faster. The APT was another one. We need to get somewhere faster, and Concorde was something we felt we could do. And I remember as a wee boy in, I don't know, early 60s, my Eagle magazine had this wonderful cutaway of a thing called the Super Caravelle. And the Super Caravelle has an incredible likeness to Concorde. And part of the problem is it emanated from a design that was put together by Sud Aviation and the Bristol Type 223, I think, which were broadly similar. And they go back to late 50s.
Yeah.
And when you've got that long gestation period, things get dated. Now, I've got a couple of questions, Fred, in chat. You refer to no engines for supersonic aircraft. What about the engines developed for military engines, e.g. the Raptor, the F-35? Well, they're kind of later. And another one says you mentioned composite materials. What about steel? Which is not a composite material, I guess, but what about steel? Because the American SST was steel, I think, wasn't it?
Well, it's basically just too heavy for its strength. Yeah, it's just too heavy.
Yeah. And the other engines,
even if you use the strongest possible steels, and I mean, I think we were talking the other day about the T188, was it?
Yeah, T188 was stainless steel.
Which was intended to fly at Mach 2.5, and that was in a martensitic stainless steel, and it was supposed to show us the problems of supersonic flight. I think that was all tied in with the idea in the 1950s of building a supersonic bomber.
And of course, part of the thing we had with military engines, you talked a lot about the Vulcan and the Olympus, but of course the Olympus 22R was the engine that was going in TSR2. And, you know, again, the development of the Olympus into a reheated engine was driven mostly by TSR2, which of course didn't have a lot of service experience.
Well, I think I wrote to you about this. My impression is that the TSR2 didn't require the power that the Concorde needed.
Yeah.
As the weight of Concorde went up and up and up, because of this square root thing, whereby you double the weight of the aircraft, you need 4 times as much power to get it down the runway and into the air, because effectively the acceleration is going to be slower because of the weight, and also because the takeoff speed is going to be higher.
Right.
It was why they suddenly decided almost one day that we have to have reheat on the Olympus, and there is a paper in the discussion to a paper I have. Somebody says the idea of a reheated takeoff is absolutely crazy, and that's because of the noise issue.
Okay, another one from the chat. Oh, yes, it says, for the market supersonics target, sort of ultra first class, I suspect the fuel consumption per mile is similar to the private cabins found at that level, not to mention the onboard shower with 2 dedicated attendants found on the Emirates A380. A tiny market, but a very wealthy one. Also, a lot of work going on with aviation biofuel, with Nestian people, and renewable methanol-based aviation fuels with Exxon. That's a comment, really, I think. Interesting.
Well, all I would say is that the Greens will just simply react to the high fuel consumption. Biofuels, unless they're going to be ammonia or liquid hydrogen, add to the amount of carbon going into the atmosphere. It takes a couple of 100 years from burning a biofuel for the trees to grab that carbon back. The idea that the carbon goes into the atmosphere and the grass next to the grass that's growing on the airfield steals that carbon back immediately, well, it literally is for the birds.
Right, agreed. Now, Brian Rice is saying, I'm pretty sure the contract between the UK and France stipulated if either party pulled out, they would have to reimburse the remaining party for the full cost incurred to date. That made the partnership almost indissoluble. And that is true. That's certainly true. You know, the Concorde Agreement really did stop any of these things pulling out.
It was the British that insisted on that.
Indeed.
They didn't trust the perfidious French. Yeah.
Of course not. Michael Grace has got his hand up.
Airport noise was quite a problem. Air France trained its Concorde pilots at Shannon, and I used to go to meetings there on a fairly regular basis. And the noise, how the people in the town lived, I have no idea. They would do touch and goes, and it was, you know, every few minutes they'd come around, do a touch and go away, and the noise really was an issue. And I think would have been another, in addition to the sonic boom, would have been another environmental objection to Concorde.
Well, of course it was. I mean, the people in New York were objecting to it. The mayor of New York, or whoever it's called, was objecting to it, and it was all made out to be an American conspiracy. But the standards for flying into New York were based on piston engine aircraft, which actually, when you have piston engines pushing out 3,000 horsepower and 4 of them and huge propellers, the noise is extremely heavy. I mean, I'm sure a lot of you have had Lancasters flying over you at air shows and know how noisy they are. Well, those American planes, piston engine aeroplanes, were twice as heavy and had twice as much power. So all that the mayor of New York was applying was the rules as they were. And Concorde managed to sneak through by having a carefully arranged takeoff path, which actually added to its fuel consumption.
Okay, another one online says, I gather that Boom have found a new aircraft engine manufacturer for their aircraft, but I can't remember who. So I think
neither can I.
No,
neither can they.
Okay, and Brian Rice, you mentioned almost in passing that Concorde should not have been built in Bristol. Now, I noticed that. I wasn't sure what you meant, Fred. What was the issue of Bristol, and was there a viable alternative? My recollection, it was originally Bristol Aeroplane Company was involved.
Yes, it was.
Well, I think Bristol, I mean, that they'd had the Britannia. I mean, that these were planes were delayed. There were other planes that were delayed, and when they decided to have it at Bristol, I thought, oh,
Well, no, it was Bristol Aeroplane Company was the partner with Sud Aviation originally before British Aircraft got formed. And Concorde was not delivered until after British Aircraft Corporation become.
yeah,
British
but it was built at Bristol.
Yeah.
That's what I'm saying. Is that
Well, it was built at Bristol because of the sharing of work, basically. So there was a work sharing arrangement within British Aircraft and Sud Aviation as to who had which share of the airframe, and between Rolls-Royce or Bristol Siddeley engines originally and Snecmar, and the work share on the
but
engines.
the engine side, I think, was okay. I mean, Bristol
Yeah,
engine.
but there was also an input from Snecmar, and a lot of the interest that we really ought to look at sometime is the value of the design of the cowling, and particularly the intake and exhaust routings, because that gives a lot of the thrust.
Yes, quite. I mean, Snecmar had apparently got this expertise on afterburners, which we didn't seem to have in Britain, and that was a crucial aspect.
Well, with any joint projects, it's work share. Anyway, Clive Ellams has come in. In 1955, I was employed in the design office of Avro to work on the Avro 730 supersonic bomber, which was planned to be built of stainless steel. I never did work on the 730, but there were many unsolved problems with the materials and construction when the project was cancelled in 1957. So that's all part of the Duncan Sands missile theory.
That's right. Yes.
Well, I think you said, I think you saw my earlier talk, you said something about the stainless was not pure stainless sheet, it was some kind of corrugated material or honeycomb.
Well, it was
honeycomb?
It was going to be constructed of this honeycomb sandwich, which I can't remember what the grade of the material was supposed to be, Fred. It's all so long ago. But it was supposed to be constructed of this sandwich type arrangement, where you had two sheets, and in between you had a honeycomb type core made out of metallic foil, which was stood end on to the two sheets.
Yeah.
And the whole thing was supposed to be brazed together by in a high temperature oven, with the parts secured in a huge jig to stop them distorting, and apparently there had been laboratory trials which on small size samples had worked beautifully, but when they tried to scale the process up, which involved possibly having two stretch forming dies for the inner and outer skins where there was double curvature, had to be and they had to be formed separately and then put together. Apparently it did not work, and they were not actually able to scale it up to a workable deal by the time the project was cancelled by the Sun's white paper in 1957.
Yeah.
The other problem we find with sandwiches with honeycombing is that if you have a curved section, don't need double curvature, just a single curvature.
Yep.
As you roll the honeycomb round, it rolls up
Yes.
in the other direction.
Yes.
And you have to do some sort of clever stretch forming while still retaining the stability of the honeycomb.
That's
And that
right.
was always the problem we had with the cowlings on the L1011 for the RB211.
Well, the Avros had done an aeroplane earlier on in aluminium alloy, which never got to the stage of flying. But it had been done in aluminium alloy sandwich, which of course was a much simpler proposition in the sense that it was
You could bond it.
it was just glued together rather than being brazed. But the problem that they did discover when they were working on that aeroplane was that if you wanted to modify it by putting in a bit of kit you hadn't thought of in the first place, you were in real dead trouble, because unless there was a solid bit in the honeycomb pre-positioned, all you were going to do was, when you tried to fasten something to the honeycomb, the inner skin of the honeycomb, say, was to
Pull it apart.
pour and spoil the integrity.
But doesn't the rudder of Concorde have something like that?
Yeah, it does.
Oh, yeah, you can get away with it in limited areas. I mean, the outer elevons on the Vulcan Mach 2, for example, are sandwich construction.
Really?
Yes.
I also, Fred, in my collection of things my sticky fingers got hold of, have the 20 small volumes of the Concorde engineering manual,
Oh,
which somehow I liberated.
but can I say something about this kind of thing?
It's theft, yeah.
I've got this kind of thing from the gas industry. What happens to it when I pop my clogs? I mean, there seems to
We've
be
been asking that question again and again in the society. It's about what these things actually do, and the problem is these things that are probably the last copy available, actually, in some cases. And I had a lot of research reports from my father in the mining industry, and I had great difficulty finding anybody that would take them, because the museums didn't really want deep technical stuff. I suspect it doesn't exist in many places, but you felt it really ought to have some residual value somewhere. I don't know.
I mean, absolutely. If you found something like this from the 19th century as a researcher at a university, that would make your career for the rest of your life.
You get a PhD on it.
Oh, you'd go higher than that.
Science Museum Library?
Maybe.
Maybe.
Frank, you're obviously going to give us the answer. Frank, you're muted.
You're muted, Frank.
Right, back again. I was about to say there was a huge row about 15 years ago when the National Archives said they were no longer going to take publicly generated research reports and engineering reports and technical reports because they just didn't have space to take that. I mean, they accession a mile a year of paper as it is. So I mean, I think one solution to that problem would be to digitize the whole lot and put it up on a website that's pretty robust. So when I hope not in long term you're no longer around to look after them, at least they have an afterlife. But I think that's the only thing one can do, since clearly libraries and museums and archives aren't willing to take this sort of really important material.
Yeah, good idea. But I think the problem with digital archives like that is what happens as versions change and who's going to keep them updated and so forth. And I know the BL and people spend a lot of time on digital legacy. It's one we ought to have a session and really get into as a society, possibly, because I suspect we're all a generation which
I've got sticky
the habit
fingers.
was that you kept things with you, and I think that's probably something we've lost.
Yeah.
I mean, I think it's certainly something for inter-society discussion, because it's not just us who are being badly affected by these policy decisions over which we have no control.
Yeah.
Well, do you think we've reached the end of the road?
I think so. I'm just reading things coming from Peter Turvey. Have to sign off now, but thanks for a fascinating takedown of this engineering icon. P.S. Used to watch the evening Concorde coming in when walking down Exhibition Road to the tube station. Yes.
Yes, it was lovely. I mean,
Yes, it was pretty, you know.
It was pretty punctual. I mean,
yes, it was amazing. 6:30 every evening.
I do remember my chairman at Lloyd's Register sitting down at lunch once in the senior dining room and saying, "I've just come back from on Concorde today. That's my 6th time this year." And everyone going, "What?" But he obviously thought it was perfectly reasonable to fly backwards and forwards on Concorde. You could argue with the benefit of hindsight whether that was a sensible decision for senior and expensive people to be flying around on what basically had a hazard lurking there waiting to happen. But there you go. Okay, I think we've exhausted questions for now at least. It's about the sort of time we would normally wind up if we were sitting in the gallery. Thank you for everyone who's attended, and most of all, thank you, Fred, for an excellent talk, well prepared as we would expect, and a good discussion. So I think we've done pretty well for the evening. So thank you all.
Thank you, Dan. Thank you, Dan.
You, Dan.
Yeah, thank you, Dan.
And